Good day everyone, I am Edric Luis G. Ato of ID 121 and I'll be teaching ENGMEC3 LQ2. The topics to be discussed in this video would be about shear and moment equations as well as shear and moment diagrams. Let's get right to it. For this problem, it is to say we are supposed to write the V and M or the shear and moment equations as well as drawing the shear and moment diagrams. So the first thing we have to do always is to draw the free body diagram. It's 1.2 kilonewtons. This is a uniformly distributed load. 1.5 kilonewton per meter. And this is a counterclockwise okay, so here as we could see, this is our free body diagram. Let's add the distances as well. This is 0.6 meters, this is 1.2 meters, 0.8 meters, and 1.0 meters. Now actually in this free body diagram there could also be an AX here, but if we get the reactions, if we do sum of forces along x is equal to 0, this is simply going to be equal to a sub x. Therefore a sub x is equal to 0 and we can erase a sub x from our free body diagram. If we add moments at a to be equal to 0, we would get minus 1.2 kilonewtons multiplied by 0.6 meters. We are taking counterclockwise to be positive. So since the 1.2 kilonewton load will have a clockwise rotation, it's going to be considered a negative. Next is the 1.5 kilonewton per meter. We have to multiply that by 1.2 meters to get the force. And since the forces are considered to be acting at the centroid, we're going to get the centroid by getting 1.2 meters over 2, and then we add the 0.6 meters from A. The 1.5 kilonewton meters also get a clockwise rotation, so it's negative. We also have a moment of positive 1.44 kilonewton meters because it's clockwise, and then we add our reaction force By multiplied by the sum of all these lengths. It's 0.6 plus 1.2 plus 1.8 plus 1. That is going to give us 3.6 meters. So solving for By is equal to 0.4 kilonewtons upward. Let's place that in our free body diagram already. Next is we sum forces along y to be equal to 0. That's going to simply be Ay plus By. It's 0.4 kilonewtons minus 1.2 kilonewtons minus 1.5 kilonewtons per meter times 1.2 meters. We're going to get a value of Ay to be equal to 2.6 kilonewtons upward as well. So let's place that value in our free body diagram. 2.6 kilonewtons. Now, we're going to have to section each part of this diagram. So one section should be in between two loading cases. So let's have this as the first loading case, second loading case, third loading case, fourth loading case, and fifth loading case. So it's the first to second first. So it's 0 is less than x is less than 0.6 meters. Our shear equation is simply going to be 2.6 kilonewtons. And since it's going upward, we're going to place it as positive. For the moment equation, we are going to do 2.6 times x. Take note that our section would be from here. So this is our x value. So this would be 2.6 times x. We need the moment from here. 2.6 times x. And since this is going to make a smile, this is also positive. Next is, let's get a section that is 0.6 meters which is less than x, to 1.8 meters. So simply stating, this is in between 2 and 3. We're going to get the shear equation by plus 2.6 minus 1.2 minus 1.5 kilonewtons per meter times x minus 0.6. The reason why we have an x minus 0.6 here is because we want only this distance. Let's call that y. And y would be equal to x minus 0.6. We could further simplify this equation so that this would become 1.4 minus 1.4 minus 1.5 times x minus 0.6. To simplify that even further, to get our final answer, this is going to be 2.3 minus 1.5x. For our moment equation, this would be plus 2.6x minus 1.2 times x minus 0.6 minus 1.5. The reason why I'm placing this as minus is because if we try to bend it, it would look like it's going to bend like a frown. Frowns will be considered negative here. So this would be the loading equation. Take note that this would be your force. This term would be the force, and this term will be your distance. Take note that the x minus 0.6 over 2 is the centroid of your uniformly distributed load. So simplifying, we would actually get 2.3x minus 0.75x squared plus 0.45. This is actually correct because if we take its derivative, we would get the shear equation, which is what we wanted. Next is 1.8 is less than x is less than 2.6. So we're going to get a section in between 3 and 4. For the shear, it's going to be plus 2.6 minus 1.2 minus 1.5 times 1.2. It's not x minus 0.6 anymore because we actually already surpassed. We already passed the entire uniformly distributed load, so it is now, it's going to be maximum. This is equal to negative 0.4. For the moment equation, we have plus 2.6x minus 1.2 times x minus 0.6 minus 1.5 times 1.2, this is your force, times x minus 0.6 minus 0.6. Now, the reason why we have two 0.6s here is because one is going to be the centroid of the force and the other is the 0.6 meters initial. So simplifying this, we would get negative 0.4x plus 2.88. Once again, we can verify this by getting the derivative, and since it's equal to our shear equation, we have a correct answer. Then our last configuration is 2.6 to 3.6. The shear equation does not change, so it's still negative 0.4 since there are no external forces. And lastly, or external loads rather, our moment equation is plus 2.6x minus 1.2 times x minus 0.6 minus 1.5 times 1.2 times x minus 1.2 minus 1.44. We have an external moment here that is counterclockwise, and since it's making a frown, it's going to be considered negative. So this would be equal to negative 0.4x plus 1.44 when simplified. With this information, we can now actually draw the shear and moment diagrams. So let's place them like this. Draw this. There we go. Now, I'm going to be using red for our shear. At this point, we're just going to increase by 2.6 kilonewtons. Then what we have here is we don't actually have any loading, any uniform load from 1 to 2, but then we suddenly drop at 2. 2.6 minus 1.2, this is going to be 1.4 kilonewtons. Next is we drop even further from 1.4 kilonewtons to negative 0.4 kilonewtons. Why is it negative 0.4 kilonewtons? Well, lastly, we're going to be multiplying 1.5 by 1.2. So this would become 2.6 minus 1.2 minus 1.5 times 1.2, which would lead us to minus 0.4. Now, the next loading situation for shear would actually be at the very end, where it goes back to 0 kilonewtons. So this will be our shear diagram. As we could see here, there is a point where it intersected the x-axis. Let's call that point x, because we're going to look for the value of x. The value of x we could actually get using similar triangles. Similar triangles would state na the base of the triangle divided by its height would be equal to a constant because they are similar triangles. So the base here would be 1.2 minus x, and then the height would be 0.4. Solving for x, we actually get x is approximately equal to 0.933. And this is actually very important when we draw our moment diagram. Now, it's really important to not forget the additional x right here. Now, let's go from here. At point 1, there is no external moment, so it stays at 0. But at point 2, we now have an area underneath this graph. The area is considered to be 2.6 kilonewtons across 0.6 meters. So, it's going to increase uniformly to about here, which is going to be 1.56 kilonewton meter. Next, here we have a triangular area with the base equal to x, which is 0.933, and the height equal to 1.4. So getting the area of the triangle, we are going to be getting an additional 0.5 times 1.4 times 0.933. That is going to be plus 0.6531 from our previous. So adding that to our 1.56, we actually get a value of 2.21 kilonewton meters. Now, how do we draw this diagram? This is the crosshair method that I would like to teach you. On the left side of the crosshair, we have those that are decreasing in value, and on the left side we have the increasing value. We have these symbols like here. So this is the crosshair method. So the decreasing and increasing here are only for the absolute values of the heights. So for example, here this goes from 1.4 to 0. So it's decreasing in value. So since it's also positive because it's at the upper side of the horizontal line, we are going to be using this quadrant. So the graph will look like this. Take note, this is a second degree function. Next, we also have another triangular area with a base of 1.2 minus x and a height of 0.4. So we are going to subtract 0.0534 from our previous. So it's 2.21 minus 0.0534. We get approximately 2.16 kilonewton meters. Now, it says here that it's from 0 to negative 0.4. Now, we would think that it is going to be decreasing.6However, in this case, it's going to be increasing. Why is it increasing? Because we are going to look at the absolute value. The absolute value of negative 0.4 is 0.4. So essentially, we're going from 0 to 0.4, which is increasing. Since it's below the horizontal line, it's a negative number. So we're going to be using this quadrant. So the graph will look like this. Once again, this is a second degree function. Now we have a rectangular area here with a base of 0.8 and the height of 0.4. So we are going to be subtracting 0.32 from the previous value. So 2.16 minus 0.32, we have 1.84 here. 1.84 kilonewton meters. This is going to be a straight line. Then we also have an external moment of 1.44 kilonewton meters, so we subtract 1.44 from 1.84 to get 0.4 kilonewton meters. Lastly, we have another square area, rectangular area here with base 0.4 and with base 1 and height 0.4. So we subtract 1 times 0.4 and we would go back to 0. So we start from 0, then we end at 0. And that is how we know that we have successfully completed our shear and moment diagrams. Thank you so much for watching. If you've learned anything, you may also avail syntax tutorials by scanning the QR code flashed on your screens. Once again, this is Edric Luis G. Ato from Syntax, paving your way to excellence. Thanks for watching.